Colloquium. Today we're very happy to have Eric Finster talking to us about Dependentopes and higher generalized algebraic theories. So please, Eric, whenever you're ready.
Okay, great. Thanks. Thanks very much for the invitation. It's a pleasure to be here. Yeah, the work I'm going to talk about today is very much work in progress. So there are many open questions and so on, but I thought I would go ahead and share it anyway. I've done something dangerous, which is find a new approach to how to describe it and try to present it today. So we'll see how that goes. But the basic premise here is what I'm interested in is what I would call higher algebraic theories. So just to sort of put ourselves on the same page, a sort of classical picture of an algebraic theory is that it's specified by giving some set of sorts and a set of operation symbols together with a set of equations. So the kind of thing I have in mind here is the theory of groups, the theory of monoids, the theory of rings, this kind of thing where you open up a book and you see a list of axioms, the various carrier sets, sometimes multiple carrier sets, the operations they're supposed to have, and the equations they're supposed to satisfy. So in higher algebra, we'd like to do the same thing, but we'd like to replace all of the sets above with homotopy types. And there's sort of a long history of wanting to do this in the algebraic topology community, where hard problems in algebraic topology, like calculating homotopy groups of spheres, involve understanding structures, algebraic structures up to homotopy. That's a long-standing project, I think, in algebraic topology. But more from my perspective, I'm now in a computer science department, and I've thought quite a lot about homotopy type theory and the connection between homotopy theory and Martin-Löf type theory. And this perspective is slightly different. It kind of proposes that homotopy theory has a completely logical reading. That reading being that when you work in a constructive system for mathematics, where proofs are first order, are objects of the system that you're manipulating, then proofs of equality are data, not property, like they are in sort of usual foundations. And in particular, proofs of equality are themselves subject to equality. They need not be unique, and so on. And the picture that sort of emerged from this, from Blavatsky's sort of looking at Martin-Löf type theory, and some other people as well, Thomas Streck and so on, in the 2000s and maybe a little bit earlier, was that one way you could interpret what was going on in constructive mathematics, where equality had this weird thing, was that it was really a theory of homotopy types. And this sort of, I think, puts a new spotlight on the need for us to understand how to do algebra on arbitrary types, on types which we don't assume to be set truncated. And so that's the kind of thing that I'm interested in, studying algebraic structures on homotopy types. I think it's probably worthwhile to just give one example. Maybe this is sort of well known to people here, but of when this happens, when you actually have a theory where the operations of that theory are non-trivial. They're not a set of operations. There's a real legitimate space. And the first example comes to mind is the theory of what are called, in the homotopy literature, E2 algebras. So in this theory, there's a single sort, so we're not going to worry about the sorts. But the operations of arity n, there's going to be a collection of operations of arity n for every n. And they're given by the space of configurations of n little disks inside a larger disk. And when I say the space, what I mean is you should imagine that every time I draw the inside disks in a particular place, I have to remember, if I want to use, if I want to point at things, I do this, right? Yeah, there we go. Every time I draw one of the little disks inside, you have to imagine that I can move it around, and moving and wiggling the little disk inside of the big one, moving all three of the ones that you see, for example, in this picture, is moving around inside of that space. And these operations can be sort of composed with each other. This would be the analog of like substitution in a theory. We can substitute terms. The terms of our theory are these configurations. We can substitute them into each other, because if I have an operation of arity 2 over here and one of arity 3, and then I have an operation of area 2, I can sort of substitute these in, glue them in, and I get an operation of area 5, where I have 5 disks sitting inside here. And of course, this all kind of needs to be up to homotopy, because if you want to fix a scale or something like that, after you substitute them in, they won't be the same size, and you need to rescale them. So this theory is really better thought of as the homotopy types of these spaces. And up here in the corner, I put an example of the fact that if I look at the space of operations of arity 2, and I imagine those two circles, well, I can put them at one point and then twist them around each other once, and I'll get back to the same point, and that's a non-trivial loop inside of this space. So this space definitely is sort of not a set, because it has this non-trivial loop inside of it. And so this theory, it's a kind of higher algebraic theory, and its models are well known. It turns out that if I fix any space and a point in that space, and I look at the spheres that live in that space based at that particular point, then that space, the space of those spheres at a point, inherits the structure of an E2 algebra. And moreover, there's a kind of converse to that, which is that given any E2 algebra, I can cook up a space such that its second homotopy, its second loop space, is that algebra structure. So these En, and you can actually generalize this for any n. These algebras play a crucial role in homotopy theory, because they're exactly the structure that one sees on a space which is the homotopy type of a double loop space. Okay, so this is why these kinds of higher theories come up in homotopy theory for characterizing spaces and structures on spaces up to homotopy. Okay, so there's a real there are many more non-trivial examples of this phenomenon of having an algebraic theory where you want to understand the operations as having a sort of space-like structure. All right, so that kind of, I want to now arrive at the question of like, well, then what is a higher algebraic structure? And one way to sort of, when I have a particular structure, is to understand a sort of categorical model for that class of structures. And by class of structures, I'm going to mean what kinds of structural rules we allow. And maybe I'll say a little bit more about that. So we often want to turn like a particular theory, like E2 algebras, into a mathematical object, and then describe the class of objects that arise from a particular class of theories. And so very often from a sort of syntactic presentation, like a syntactic presentation of what are groups or what are rings or something like this, we can cook up a mathematical object, so that oftentimes a category, but as we'll see in this talk, I'm going to go outside, in some sense, the world of categories, so that models can be sort of understood as homomorphisms of that structure. This is the classic picture of Lawvere semantics, functorial semantics of algebraic theories, which is you cook up a category. Lawvere's original version was for finite product categories. You view finite product preserving functors into sets, and those are exactly the sort of models of your theory. So when we have finite product theories, we're sort of allowed to have, and I give here examples of different classes of categories which correspond to theories where we have more or less structural rules. So in finite product theories, which are kind of the theories I was talking in the beginning, groups and rings and fields and so on, not fields. You have operations, and these operations can forget or duplicate inputs, and that's where the product amount comes from. And then you have more general finite limit theories, where you're allowed to have sort of partially defined operations, because instead of being defined on a product so that an operation has arity 2, it might be defined on a pullback so that it has arity 2 satisfying a condition. And then you have other things more general, like toposes, which capture geometric theories, where you're allowed to have sort of inputs from external sorts. And you have operads, which actually, which the E2 example is an example of, which are kind of restricted theories, where your operations only ever compose, but you can't forget or duplicate inputs. So these are kind of very weak. And all of these can be understood as mathematical objects in their own right, and they correspond to classes of theories. When we have a sort of theory that we understand, or a class of theories that we understand corresponds to a particular categorical structure, then we can often kind of very quickly pass to the homotopy version of that kind of a structure. And by just kind of repeating the analog of what we said before in the theory of infinity categories. And so because there's this very well developed, very well understood theory of infinity categories, which are essentially categories where the objects and morphisms are homotopy types, sort of a higher version of categories in the sense I talked about before. And because we have this good theory, we can kind of repeat and get, we can kind of put an infinity everywhere and get a good answer to what is the question of what is a finite product infinity theory. What structure should that have? Well, it should be it should correspond to infinity categories with finite products. And same thing for finite limit theories. I can consider infinity categories with finite limits and limit preserving functors into not sets anymore, but into homotopy types or spaces. And this will be a good picture of what is a higher algebraic theory, which allows partial operations and so on. And we also have infinity geometric theories because there's a large and well understood theory of infinity toposes. So in some sense, we have very good answers to what is an infinity finite algebraic theory coming from category theory. But I want to sort of talk about a version of this for what are called generalized algebraic theories. So these are theories that they have the same kind of strength. I'll stay with the classical version for now. They have the same kind of strength as finite limit theories, but they use a kind of different style of presentation. They use the style of presentation that we see in dependent type theory. And what that means is we're allowed to have sorts and operations which may only be defined in the presence of sorts of elements from sorts that we've already defined. So, I mean, the classic way to see the difference between sort of a finite limit presentation of the theory of categories and what I've done here is the theory of categories, by the way, but I maybe should have written that. I've sort of given the two ways you might describe the theory of categories. You might say it's a collection of objects and morphisms together with a source and target, and then a composition given on the pullback of the source and the target, and satisfying a bunch of equations and laws and so on. So this gives the kind of picture of there are objects, there are morphisms, and there's a whole bunch of operations satisfying equations. And then you have the dependent type theory presentation where you say, okay, there's a sort or a type of object, and given two elements of that sort, there's a sort of homomorphisms between them. But this sort, hom, is only defined when you've already given me an x and a y. And so this is the kind of structure you see when we're talking about dependent types. So hom here would be dependent types. And since I'm sort of really interested in this connection between higher algebra and dependent type theory, I want to sort of think about what higher versions of generalized algebraic theories might look like. All right. By the way, I should have mentioned that I'm perfectly happy to take questions if people have questions. So so if you want to jump in and anything's not clear or you want clarification, just fire away and I'll do my best. All right. So this class of theories, generalized algebraic theories, they have a nice ordinary categorical semantics. And we can, in a certain sense, play the same game I was saying before. Because we understand the sort of mathematical object, the categorical object that corresponds to this theory in a nice way, we can kind of infinity it for free by relying on this theory of infinity categories. So there are a couple, in fact, there's a lot of different like sort of categorical semantics for dependent type theories. You can go look. I think there's a nice paper which compares a lot of them are known to be equivalents in various cases with various restrictions. There's a whole web of different things. I'll focus here on one which generalizes very easily, which is the picture of generalized algebraic theories as natural models. And so what this is it's a category of contexts together with two presheafs, and with a map between those presheafs. Alpha is supposed to live in the presheaf category on C, and it's supposed to be a representable map. And what representable means down here is that if I have, oh, I should have said alpha right there. If I have my alpha here, if I have an element, a type in a context, and by type in a context I mean an element, a map like this, where Y is supposed to be uneta, which is the image, the uneta of a context. So this would be exactly an element of that presheaf at that context. The presheaf is supposed to give the types valid in that context, and they may change depending on the context. That's the whole notion of dependent types. And the idea is that if I then pull back this map, that this pullback here needs to again be representable, and it be representable by an object of C. The pullback needs to be equivalent or isomorphic to uneta of what we call the context extension. And this universal property corresponds to the fact that if I have a type, I'm allowed to suppose that I have a variable of that type. And in this picture, the sort of judgment style dependent type theory I was presenting gets encoded as follows. The sort of context that precedes the judgment becomes an object of C. That's what I've written in C. The type that you conclude is well formed in this context is an element of the type presheaf, and the term that you consider to be well formed in that context is the element of the term presheaf. And then the natural structure that you have on this category and these presheafs expresses the structural rules that we expect any generalized algebraic theory to have. So for example, the fact that these are presheafs means that if I have any morphism of C, which is supposed to be a substitution between contexts, that I can pull back a type into another context by substituting in all the terms and so on. And I can do the same thing with terms. And this representability criterion says that I have a context extension operation so that I can suppose that I have new elements. Okay, so this is a very nice, I always say this is a very nice presentation, a way of understanding what a dependent type theory is, a mathematical model of a dependent type theory. And I can, again, as I say, I can kind of just stick infinity everywhere here, and all of this makes sense. So supposing that I know what an infinity category is and what an infinity presheaf is, which is a presheaf on that category taking values. The two presheafs correspond to the types and the terms valid in any context. That's what I've tried to indicate right here. So in a context, I'll have a collection of types which are valid and a collection of terms of those types. And if I have a context and a type in it, the fiber of this map alpha is supposed to be the collection of all terms that have that type. That's the way to interpret the two presheafs here. Right. So as I was saying, so you can kind of just repeat this very quickly and arrive at a notion of what a higher generalized algebraic theory is by just putting infinity everywhere. And so people have done this. In fact, I think there's a paper of Ramura and a couple of people who take this as a definition of what is a higher generalized algebraic theory, defining it by its sort of mathematical incarnation, generalizing it to the infinity world, and there you go. So that's great. What about this approach is that it kind of loses the connection with syntax. And the connection with syntax is kind of what makes generalized algebraic theories an interesting thing in the first place. The fact that we can implement them on a computer, we have very well-known routines for type checking. In particular, Martin-Love type theory is presented as one of these generalized algebraic theories. And in fact, I think it's the inspiration for their definition. And it tends to be something which is very easily manipulated on a computer, and many of the most popular proof assistants are sort of written in this style, in style of dependent types. And so you start out here with kind of the syntax presentation of a GAT, and you turn it into this mathematical model. The one that I've presented today is this natural model, and then you realize that I can repeat all of that in the world of homotopy coherent mathematics by just kind of replacing everything with infinity category, and all the definitions that you need are found in the literature. And the sort of question is what goes, or a question which has always bothered me is what goes over here. if we're sort of doing on this row, if we're sort of doing categorical logic, where there's a sort of connection between logic or algebra that we write and the mathematical models we make, then when we pass to the higher world, that's in some sense been like broken a little bit. And so what I'm going to sort of continue presenting today is my attempt to kind of like bridge that gap, is to go in the direction of understanding what is the syntax of higher logic that goes along with these higher models that we can produce. So to give an analogy, I want to give a little bit for what I'm going to do. I want to take the case of operads, and operads are kind of very, as I said, they're very basic algebraic theories because they don't have that much structure. They don't have, you can't add and forget variables, and all you can do is compose operations. So they're somehow the only structural rule of an operad is what we would call substitution. And there's actually a number of different approaches to defining infinity operads that you find in the literature. So the one given by Lurie, who laid down a lot of the sort of groundwork for this, is kind of the style that I was talking about before, in the sense that it starts with the fact that there is a good theory of infinity one categories, and it leverages that theory to say what an infinity operad is in terms of infinity categories. And Lurie's answer to this question is, I'm not going to trot out the whole definition. I only have kind of a vague, I don't think I've ever like memorized exactly all the definitions, is that it's an infinity operad is going to be an infinity category itself, equipped with a map over the infinity category of finite pointed sets. And this category has a certain factorization system, and you add some conditions, essentially saying that you have various lifting properties with respect to the morphisms and their factorizations in this category. I think this is called the inert active factorization system. There's kind of a lot of literature on this, but roughly speaking, it's a special kind of functor, a kind of functor with some additional fibrational conditions. And you sort of think of the fiber over the n element set here as the operations of arity n. So that's one thing. So that's a kind of example of, I think, what I was saying before, is we have the theory of infinity categories. We can leverage the theory of infinity categories to give a definition of other kinds of algebraic structures. But there's an alternate approach. And so, by the way, if you look at the underlying data of such a thing, both things here, this is a sort of map of simplicial sets, right? So we have two simplicial sets and a map between them. Yeah, so I guess, is that, I have to think if that's actually, is there, well, anyway, I'm now thinking that what I was going to say is maybe not so different, but anyway, so there is an alternate description of infinity operads where you view them as a single pre-sheaf on a category of trees. So you can construct a category where essentially the objects are trees and morphisms are certain collapsing maps between them. And you can look at pre-sheafs on this category of trees as satisfying a kind of fibrancy condition, and those are also models for infinity operads. So here you're starting with infinity categories. Here you're sort of more adapting your definition of what an operad is to the kind of structure that an operad encodes. And you can't do much operad theory without realizing the operads are kind of like their behavior is governed by trees. And so you can view an operad as kind of like assigning a collection of inhabitants to trees, the kind of fundamental structure. And there's actually still another definition, which is the one that I'm going to sort of go to today, which is in terms of Bias and Dolan, they give a kind of another category, which I should write O, which is confusing. I shouldn't write it O like that because that's the same as the O that I wrote up there. I'll just write it O like this. Or maybe O for opetopes, or maybe OPE or something like this. And you can talk about, I think in this version, it's better to think of opetopic spaces, which is why I've written opetopic spaces right here. But I'll come back to that. And this is another category of shapes which somehow encode in a very explicit way the high trees and higher dimensional trees that express the coherences you expect to see in an operad. So this category of shapes is, in some sense, capturing exactly the structure that you expect to see, the coherences that you would expect to have in an algebraic theory of this particular type. Okay, so I just wanted to say that in this particular case for operads, we not only have this sort of natural categorical definition in terms of the theory of infinity categories, we also have a couple other definitions which are sort of more explicit. And that's what I want to sort of do for the class of generalized algebraic theories, is to develop a explicit version of this. Okay, so to do that, I'm going to give you a quick sketch of how to get to the opetopes. And I'm going to do it in terms of the theory of polynomial monads. So I think that's something which comes up a lot at the Topos Institute. So I want to start with a polynomial monad. So I'll say, so M here will be a polynomial monad. And by that, I mean it has an underlying polynomial, a polynomial being a diagram like this in the category of sets. And for this version of a theory, you think of I as the collection of sorts. You think of B as the collection of operator symbols. You think of the fiber of this map, which I'm going to assume to be a finite set, as the arity of each operation. And you think of the last map here as assigning each arity, each input, a sort. Right. And so a polynomial monad is one of these polynomials. Each polynomial, maybe I should call this the underlying of M here, is this polynomial. It's going to induce a functor from set over I to set over I, M. And M is a polynomial monad if this induced functor given by this polynomial, in fact, has a monad structure. And that monad structure can be described very explicitly in terms of the polynomial itself. It basically says that there's, for every I, there has to be a kind of trivial operation, which you think of as a sort of line like this. And it says that if you have any sort of configuration, any tree of operators, be like labeled by the B's here, that you can multiply this down and get a single operator of the correct area. So you have like a mu and a mu, and this is sort of the combinatorial structure which completely determines this monad. Okay, so I'm going to assume that this is at least a little familiar to people in this audience. Okay, so you have the category of polynomial monads with fixed sorts I, and you also have, and I'll write poly I for just the polynomials like this, with fixed sorts I as well. And I'm going to consider the Cartesian morphisms between these. Right. I hope that makes sense if people know what the Cartesian. So a Cartesian morphism here would be, if I write my polynomial over here, E, B, I, then I'm going to fix the I for right now. And then the Cartesian morphisms are the ones where I have an X, say, like this. And then Cartesian means that this square is actually a pullback square, E. And then this map goes like this. And because this is I and this diagram has to commute, that actually means that this entire polynomial over I is in fact completely determined by the map X, because the other maps are completely determined. And this is this kind of funny fact that if I fix I and look at the polynomial, the Cartesian morphisms over a polynomial, it's actually a topos. It's just the topos of sets over B. So sometimes people say this is locally a topos, I think. Anyway, so that's just that fact is going to come up here in a second. So I have polynomial monads with sorts I and polynomials with I. And there's a forgetful functor. If I have a polynomial monad with a map to M, then I get a polynomial over I, over M, it's over the underlying of M, just by sort of forgetting. I guess maybe sometimes I was writing this as the underlying of M over here. All right. Does that make sense? So everyone okay with that? Now, so here's one description, and this is not the description you see in the literature, but I'm going to give this description because I'm going to use it later. So there's this forgetful functor, right? I think that's what I just said on the last slide. And I claim this forgetful functor, and I'm remembering here that when I'm considering Cartesian morphisms, oops, I don't want that, I want to do this, that poly I over a fixed polynomial is just set over the operations. And the operations can be described for any polynomial monad as just m applied to the terminal object. So you have this forgetful functor, and this forgetful functor has a left adjoint. It has a left adjoint which says that if I fix any x on the previous page, just over here, I just fix an x which is just a polynomial over the underlying polynomial of a monad, then I can freely complete that to a monad equipped with a map to the monad that I'm starting with. And this has a very kind of explicit description. And moreover, so this left adjoint, it induces a functor on polynomial on set over M1, and this functor itself is given by a polynomial. Is given by a polynomial monad, right? So the induced functor over here is given by a polynomial monad, and that underlying polynomial monad is what people call M plus. Okay, it's the plus construction that says, because all we did here was we started with an M, we considered the fact that this had an adjoint, and then we got out a new monad, this time on set over M of 1, and that's one way to describe the plus construction, Bias and Dolan's plus construction. Okay, is that, were there any questions? There's the chat. Oh, that's old. Okay, so this is a kind of operation on polynomial monads, and all it depended on was the input of m, and we got the output of n plus, which means in particular that I can iterate it, right? I can keep going. I can do plus 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 plus. So a quick and dirty definition of the opetopes is that I'm going to define an infinite sequence of polynomial monads. Oh, I guess I wrote it here as L. Oh, that's right. Okay, that is correct. So again, this is not the way I usually present this, but I had to present it this way to make the next thing work. So so there's a way to produce a series of monads. I take M of 1, and I'm going to define Mn plus 1 of 1 to be, well, I have Mn, and I can take Mn of 1, that's its operations, and I can take the slice category there, and I have the terminal object of that slice category, which is just the identity map on M of 1. So that's a map over the operations of Mn. And now I can apply the left adjoint to that, and that gives me a new polynomial monad, because the left adjoint takes values in the category of polynomial monads. It's equipped with a map to M, but I'm going to call that Mn plus 1. And an n opetope is going to be an element of this nth iteration of this construction. And there's a nice sort of diagrammatic picture where opetopes are generalized trees. And I've always thought of them as kind of generalizing the idea of a syntax tree into higher dimensions, where the operations have syntax trees from gluing them together, substituting together, and then the relations which go between operations also have syntax trees which get glued together. When I have relations, they're between multiple operations as an input and a single operation as an output, and those can be composed themselves. So it's a kind of it's a nice picture where you see the higher coherences arise as syntax trees iterated in higher dimensions. So that's what I mean with it has a kind of a nice connection to the idea of what I would think of as higher dimensional syntax. Okay. Now, I'm going to try to play the same trick. Okay, I'm going to try to play the same trick for generalized algebraic theories. And so the way I'm going to do that is I'm going to rely on some work of Richard Garner back in 2015, where he gives this really kind of nice alternate presentation, mathematical model of what is a dependent type theory. So this is kind of in contrast to the categorical models that I described before, like Steve Wabby's natural models. This is a kind of more, I think it's a little bit closer to the syntax that we actually write and we actually manipulate when we write down a generalized algebraic theory. Because what we manipulate in practice is judgments. So we have these typing and term judgments, And the generalized algebraic theory is really the collection of all the valid judgments, okay? And so Richard's approach is to see the judgments of a generalized algebraic theory as elements of a certain presheaf, okay? And so we cook up a category here that I've drawn over here called H. It just has this infinite sequence going up here, and oops, and then there's a single arrow branching off at each point right here. And that's it. That's my category. So it's just there's nothing really to compose. There's not much to say about this. It just goes off forever. And I'm going to think of presheafs on that category. And so down here, I sort of drew, although it's not very pretty, what you should think of in this model, the elements of those presheaf at particular objects. So 0, the elements here are going to be the closed types, the types that are valid in the empty context. And the elements right here are going to be the closed terms, that is the terms of type A, which are valid in the empty context. In other words, don't depend on any variables. And the projection maps here, which I get when I take a presheaf, are going to just take a term and assign it its type. And furthermore, as we climb up the ladder, what we're seeing is judgments of types in context. So you should think of an element here, you should picture it as a judgment of a type which is valid over the type A, where A is the image of this judgment projecting down into the next level. Okay, does that make sense? Each time the projection is going to throw away the type here and just return to me the last type that I saw, which is A. And similarly, when I have terms of this type in this context, they're terms depending on a variable A of a type depending on a variable A. This term B of A is going to project down to this B of A. So the fiber of this map at a chosen type is the collection of terms of that type. Okay, does that make sense? So this presheaf category here is cooked up exactly to encode just the shape of type and term judgments in a dependent type theory.
And is there any relationship between the fiber, the A colon A on the upper left and the A colon A on the lower right? Lower right, A colon A, arrow B, like in one, yeah.
No, this is just meant to mean that by writing it as A over A, all I mean is that this is an element here who projects onto A, and here by writing it has type A, I just mean this is an element which projects onto A, but these two are completely independent of each other.
Right. Is it kind of like the one on the left is more like sigma and one on the right is more like pi?
I see. Maybe you mean that like here, I mean A is not a variable, it's a term.
Okay,
it's
great.
An actual term. Yeah. Whereas here it's supposed to be a variable of type A. Yeah, I shouldn't have used that same.
But there's no interaction here that like I can plug A0 in and get a B sub A0 or anything like that.
That's my next slide.
Okay, thank you. Sorry.
That's my next slide, right. So the point is that this is just the judgments themselves. But in a generalized algebraic theory, the judgments don't exist in isolation. They have structural rules that we apply to them, okay? So I gave two examples. So if I have two, I keep doing that. If I have a closed type A and a closed type B, then I want there always to be a judgment that says that B is still valid if I assume I have an element of A. And this amounts to, if I'm given two elements of this presheaf down here, I want there always to be an element up here living over it, which then projects down onto A. Okay, so this presheaf, so when you see this and you think about, and here's an example of, I think, exactly what you're saying. If I have a closed type of type A and a closed term, and then I have some other dependent type, I want there always to be a closed type where I've substituted my closed term into that type. So I have this, and I have this, and I have a dependent type. Then that 3 amount of data is supposed to give me a closed type, okay? So this presheaf is not just a presheaf. For it to be a GAT, it should have all these operations. It should be a presheaf equipped with a bunch of algebraic structure. And so this is what Richard does in that paper, is he describes the algebraic structure that such a presheaf should have, and he describes it as a monad on this presheaf category. Okay, he calls the monad, well, I called it G, I'm not sure, but there's a monad on this category. And its algebras encode exactly all the structural features that you expect to find in a generalized algebraic theory. Okay. And he gives a very sort of explicit combinatorial description, which is very nice. And in particular, one nice feature that this has, which is not obvious kind of at all, is that this monad is itself the analog of a polynomial monad in this pre-sheaf category, in the sense that it's a local right adjoint, or it's familially representable, which is to say that if I look at G of 1, G of the terminal pre-sheaf, and look at its category of elements, those are the operations of this monad. And to each of those, I can associate a pre-sheaf, which is like the arity of that operation. And it happens that if I apply G to any pre-sheaf and look at its value at n, that can be expressed as the operations of the terminal pre-sheaf at n, and then maps from the realization that the arity of that operation into P. So this is kind of this is the pre-sheaf generalization of kind of a sort of polynomial monad on this pre-sheaf category. So generalized algebraic theories are sort of a polynomial, algebras for a polynomial on this pre-sheaf category, which is quite nice. All right. Now, maybe you see where I'm going with this, which is that I'm going to generalize this. The generalization is, suppose that you give me already an algebra for this thing, so a generalized algebraic theory. So it's a pre-sheaf with this additional structure encoding the structural rules of generalized algebraic theories. Well, then I have a sort of, I can consider its underlying pre-sheaf, which is just living down in this pre-sheaf category. And so this gives me a functor. If I have a generalized algebraic theory equipped with a map to A, this here in the sort of category of algebras, then I can project it down and I'll get a pre-sheaf, its underlying pre-sheaf equipped with a map to the underlying pre-sheaf of my generalized algebraic theory. Okay, so here I'm trying to repeat the story that we were doing for polynomial monads, where I started out in the algebraic category just for getting down to a slice of a pre-sheaf category. And I guess the mild generalization, I guess you could call this a theorem, although part of me thinks that this theorem is probably a consequence of something that's already well known somewhere. But so I'll call it a theorem, but someone has all the right in the world to tell me that this follows from something else, because it probably does. Is that this forgetful functor also has a left adjoint? Okay. So in other words, if you give me a generalized algebraic theory and then one of these type and term structure pre-sheafs without any structure, it's just a collection of judgments, primitive judgments, then I can freely complete it into a generalized algebraic theory, which comes equipped with a map to the one that you started with. Okay. And this functor is also familially representable. It's also a local right adjoint. So all of the slices of this category of generalized algebraic theories have these monads. This G somehow is closed under slicing. I don't know if there's a way to make this exactly precise, but that's what I wanted to say. Okay, so for every A, we get the functor, which goes from these type and term pre-sheafs equipped with a map of A to a GAT over A. In particular, it produces a GAT. I can forget the fact that it's over A. All right. So now I can play the same game that I did before, which is that I can use this to generate a kind of canonical sequence of generalized algebraic theories. I'll start with the terminal pre-sheaf of set H op. So this is the generalized algebraic theory, which has exactly one dependent type of arity and exactly one term of every one of those dependent types. You should think of this, or the way I think of this is, it's the theory of a contractible object. It's the theory of an object with a point, and everything you can do with that point always gives you the same term. Okay, so that's the way I would think of that generalized algebraic theory. And so what I can do is so that is a generalized algebraic theory, and then I can make the same definition I did before, which I'll get a new one by saying the n plus first generalized algebraic theory is L of the nth one applied to the terminal map, the identity map of that underlying thing mapping to itself. All right, so I'm a little bit out of time. I kind of thought this would happen, that I would just get to the definition. But anyway, so I can now say an n-dependetope is an element of this pre-sheaf that I get. I mean, each of these generalized algebraic theories is itself a pre-sheaf, and a n-dependetope will be an element of that pre-sheaf. An element, I mean generalized element, so element in any one of the values of the pre-sheaf. Okay, so dependentopes come together with a kind of shape, a judgment shape that they depend on, but there's much, much more than that. So the way I think of these is just like the opetopes were in some sense higher dimensional terms. You can think of these as higher dimensional judgments, or the shapes of higher dimensional judgments that are sort of being built out of the algebra that judgments are supposed to have to begin with, right? So we start with the theory of what a generalized algebraic theory is, encoded by this monad G, and we use G to generate a set of shapes, which are the shapes that sort of encode the coherent version of G, if you like. So that's the kind of trick of opetopes and the trick that I'm playing here with the dependentopes as well. Now, let me just kind of sum up. So each one of these GATs GN, it has a very explicit presentation. We start with a very simple GAT. It's the GAT consisting of just one type and one term of every sort of type, of every arity. This is very easy to implement on, say, a computer. And consequently, these GNs have also a very explicit description, which is kind of derived from what's happening in Richard's paper, but also the fact that you can reinterpret Richard's paper as his combinatorial description as elements of as particular types and terms that you can give. Anyway, all I want to say is that these GNs have a very explicit syntax which can be implemented on a computer. The result being that there's a kind of an algorithm for checking when you found a dependetope. You can sort of describe one in a complicated way, and it's a term of a certain theory that you can implement. Yeah, so that's why I say the terms of these type theories are somehow parameterizing the coherences of what a higher version of a generalized algebraic theory should be. And what I mean by that is once we replace the types and terms with spaces of types and terms, then the original monad G, which just has a bunch of equalities, is not going to be enough. When I substitute multiple times, I don't want the associative law in that space of operations to just be equal. I'm going to need an additional law to say that doing it 4 times is related to doing it 3 times in different ways, etc. The usual story that when I generalize to spaces, I need more information about the law. So what I've produced here is a collection of shapes, which I sort of put forward as parameterizing these coherences in a way that you need. And these theories, as I present them here, they're sort of there's one for every n, but they should be glued together into a particular category, the category of dependentopes, and then such that I can define a higher generalized algebraic theory as just a pre-sheaf on this category satisfying some conditions. So that's the kind of idea I have of this, and this sort of going back. This is why I was talking about operads, this version of operads, where I introduce these additional shapes which parameterize the coherences, and then I say, these are filled with spaces. You have to give me not only operations and types, but also higher types witnessing the equalities between all your operations. And if you give me enough of those so that they satisfy a vibrancy condition, then that's what I'm going to call a higher generalized algebraic theory. So I think we kind of hit right on the nose because it looks like I have about 2 minutes left. So let me stop here and sort of open it up for questions.
Thank you, Eric. That was great. Right, so we have time for questions. If anyone has a question, there's a react button with a little heart on it, and you can raise your hand or just unmute yourself. Looks like David Jazz has a question. Please go ahead, David.
Yeah, go ahead, David.
Thanks, Eric. This is really cool. I hadn't heard of this like combinatorial approach to GATS, Garner's approach there, and I'm very curious to see examples of Dependentopes. I don't know if you had any prepared slides with a picture on
Right.
those.
So I do. Yeah, exactly. So there's a certain way. So you might know I have versions of them, but I don't have ones to show you today for this version. As I said, I kind of found a better thing, which presentation, which makes them much closer to opetopes, which is what I presented today, because I think that's the right way to think about them. You can actually embed them. So this is a common thing. There's a generalized algebraic theory whose models are generalized algebraic theories. And so you can actually use this to also generate an infinite sequence, and the dependentopes live inside of that theory. So in this sense, there is an explicit syntax, but I didn't know an algorithm, but those theories are too big. So I didn't know an algorithm for isolating exactly which ones were dependentopes and which ones aren't, if that makes sense. So I have examples, but I didn't know how to say exactly which ones should count as shapes and which ones shouldn't until I found this presentation. But the side effect is that I don't have an explicit syntax to show you today, so I can't quite show you examples today. But I think it will be clear to work out from this how that looks, and I expect to have examples in the near future.
Thanks.
And I hope also, I should say, that there is an accompanying kind of diagrammatic picture to be pulled out of this. This is something that was like lacking from my previous approaches because there were too many, so I couldn't see how to make a diagram out of them. But I would love it if I could find a kind of combinatorial picture of these objects as well. And I think now that I have a really good picture of them and a relationship to opetopes, I think there's a distinct possibility that that's possible.
Cool. And when you say vibrancy condition, you mean more like Kahn than like Siegel, right? In terms of
yes. These are biased in the same way the opetopes are, so it will be more like Kahn than Siegel. Yeah.
Great, thanks, David. Kevin has his hand raised.
Thanks a lot, Eric. Very clear talk. So I'm trying to just kind of summarize the upshot. So you're proposing, and let me know if I'm understanding right. Here's a great way to give a notion of GAT that I can infinitize roughly for free, right? And so you were saying right at the end there, you were like, I'm going to make a category of dependentopes, and then precisions on that with a certain model structure will be your infinity GATs. Was there an analog of are you at all interested in or does this help produce an analog of the fibration over thin-set star kind of pictures? Are you reproducing multiple infinitizations of GATs here, or like that's your single path that you're now following through? You need the category of dependentopes.
Kind of a single path, and I would hope sort of eventually that you could make the connection between the I don't want to call it naive, but a little bit naive path of taking the category theory that you have and just putting infinity everywhere. I mean, that gives a specific model, and then this should give a specific model, and you would hope that those two are equivalent. Like back in the case of operads, for example, you have this categorical model where you use infinity categories, and then you have this more like pre-sheaf model, and they have been shown to be equivalent in the literature. I don't think this one, but this one, the dendroidal sets, and this one have been. Right. But I guess for me, the upshot of this is trying to have it's not clear to me, like I said before, what syntax one could use to describe this version of what a higher GAT is. And the dependentopes are not quite yet there in the sense of me allowing me to give a syntactic description of what a higher GAT looks like. But it's kind of on the way, if you like. It's parameterizing what the shapes of such a syntax would look like. And I would hope, in addition to this kind of semantic description that I gave, or that I proposed, where was it? Over here. Yeah, that a higher GAT would be a pre-sheaf satisfying a vibrancy condition. I hope that there's also like just a syntactic presentation. arising from this, of what it means to work in a higher GAT. Now, I expect that syntactic presentation is kind of very difficult to use in practice, but that's okay. It's more about answering the question of whether it exists than necessarily using it in practice.
Do you feel like there is such a like really syntactic presentation of higher non-dependent algebraic theories yet? I'm trying to see if there's
I kind of hope that there is. Yeah, I mean, I do think that there eventually should be. I do
but
think.
you're not saying that there already is one that you're generalizing from. You're not saying that there already is one for even the non-dependent.
Oh, that's the kind of funny thing. If I go back here and look at this, if I sort of it's not clear to me what actually it would mean. There's something really funny about this because so you can kind of implement this if you, so people have done this in like two-level type theories. Like there's this original coherence problem in type theory where we can't seem to describe really any higher algebraic structures. And there's various ways of understanding what that is. But in any case, in one way you can do it is move to a two-level theory where you get rid of the homotopy information in one level, and then you give kind of an algorithm for producing all of the types that it would correspond to this categorical presentation. In other words, you realize them as simplices and simplices of simplices and lifting and so on, and where simplicial types are something, yeah, you can use them. But the funny thing about that is that produces for you a GAT, not a higher GAT. So the higher GAT is not like a model of itself in a weird way. You're using the syntax of a GAT to describe this categorical one. But that's kind of weird because it doesn't sort of eat itself, right? So that's the other thing that I'm looking for is a model of, or a picture of a generalized algebraic theory, a higher generalized algebraic theory, which is itself a higher generalized algebraic theory in some sense. That kind of closes that loop that feels missing to me. I don't know. So those are just some random thoughts about where I'm going with this. But.
Yeah, cool. Thanks a lot.
Yeah.
Thanks, Kevin. We have Jacques Corrette wants to ask a question. Please, Jacques.
It's actually Nate who has the question here. Sorry. So on the note of syntax, it seems like we're presenting a lot of these guys, even these opetopes and operads, as pre-sheaf categories over nice combinatorial things. We do have some technology for kind of approaching a syntax. If you use like the Orton-Pitts stuff, where you essentially internally to the syntax of that pre-sheaf category and try and give an axiomatization of like an interval object or some, basic shape. So have you thought about maybe taking that as an approach, at least to sort of approach something that resembles a syntax?
So, but I guess that's a little bit different, right? I mean, because when you internalize in a pre-sheaf category, you're not making, you're actually, right. In order to do that in this case, I guess you would need to know like what the dependentopes classify, right? Because then you would need to give that object internally in order to sort of be working in the internal language of this pre-sheaf category. And in that case, when you work in the internal language of a pre-sheaf category, you kind of give up the fact that you have this explicit presentation of the objects that you wanted to work with. So there's certainly, I mean, there's a type theory in any pre-sheaf category. So the way we implement them now, even these type theories that we embed into particular pre-sheaf categories are kind of set truncated. We don't record in the notation the coherences that arise from higher substitutions and so on. We substitute them away. We reduce them away. So I guess I feel like this is going in a slightly different definition, which is that I'm trying to bring that explicit syntax back. Not necessarily because I want to use it, by the way, but because I want to have a definition of what it is so that we can prove theorems about it, right? That's more the goal somehow. But anyway.
Yep, that makes sense.
Yeah.
Chuck, I had a quick question. So we had this category H that Richard wrote down, and we have these pre-sheaves on it. Are they satisfying the representability condition of the natural?
No.
Not, right? Right. Okay.
No, context extension is kind of encoded in a different way. In some sense, context extension is Yeah, is just encoded in the fact that this diagram continues up to the left at every point.
Exactly.
It's not an operation in itself. You have all the extensions laid out for you at once in this spine.
So that is just gone from this point of view, right?
Yeah, exactly. This rephrases completely, right? So what was before substitution in types and terms, which was kind of pulling back in the categorical structure, is now just an explicit operation that's given on these elements. Yeah.
Great. Cool. Okay, I think that's all the time we have. So thanks again, Eric, for the great talk. And I'll stop the recording and stop the live stream.
All right.
Then sometimes people stick around, as I said earlier.
Stick around for a couple more minutes if anyone has any other questions.